Okay, so our motivation here was that we wanted to give a bit of physical intuition into radial quantization. So what I'm going to do now is I'm going to perform an equal time quantization on the cylinder. So on the cylinder, so on R cross S1. And so I would foliate things with constant time slices. We'll talk about what those slices look like soon. Um, and time evolution would correspond to shifting A. So that would be time evolution. T goes into T plus A. And let's maybe draw it now. Here's the cylinder. And we can ask ourselves, we can draw a point over here. Let's call this is the slice t is equal to 0. So t runs along the cylinder. This side of the cylinder is at t is equal to minus infinity. This side of the cylinder is equal to t is equal to plus infinity. And if we fix a specific value for t, that point, all points with a specific value of t, is a circle along the cylinder. So this could be a point at, I don't know, t is equal to minus 4, or minus 4. So some negative value of t. So then it appears to the left of t is equal to 0. And I could also have a constant time slice at t is equal to 4. And then it would appear to the right of t is equal to 0. Okay, now what do we want to relate this to? We want to relate this to radial quantization on the plane. So we mean on R2. Okay. And so let's first of all see what does this time translation become. So let's try to write that on the plane. Well, we know that R is equal to e to the t. So R will be e to the t. If I now shift, t goes into t plus a. This becomes e to the t plus a. And that is nothing but e to the a times by e to the t. And we said e to the t was r. So this is just e to the t times by r. So a time translation on the cylinder becomes this transformation on the plane. What is this transformation? It is nothing but scaling. We've scaled r. We've multiplied r by e to the a multiplied by r. So we've related normal equal time quantization on the cylinder now to radial quantization on the plane. So that's why we introduce this change of coordinates in this mapping. I'm trying to argue now, this is what I'm trying to convince you of, that everything that you know about equal time quantization on the cylinder through our change of coordinates becomes equal R quantization on the plane. And which change of coordinates am I using? Maybe good to rescue that and put that here so that you can keep that in mind. It's R is equal to e to the t. This is the relationship between the radial coordinate on the plane and the time coordinate on the cylinder. So if we take t is equal to 0, you can see that's r is equal to 1. So let's draw in the unit circle. So here's the unit circle, okay? And the unit circle, this black unit circle corresponds to that black circle on the cylinder. If we now look at t is equal to minus 4, well, then we've got e to the minus 4. You know, e is something like 3. So so e to the minus 4 is something like 1 over e to the 4, which is 81. So this would be a very small circle on the plane. And if we look at that red circle, which is e is equal to 4, that would map into a very large circle, something like 81. Sorry, let me take that out. So the red circle on the cylinder would map into this red circle on the plane. So what do you see? You see that equal time slices on the cylinder become equal R slices on the plane. Equal time slices on the cylinder are equal radius slices on the plane. We see that time translations on the cylinder become scalings on the plane. And this should be enough to convince you completely that equal time quantization on the cylinder maps into radial quantization on the plane. And it's radial quantization that we're used to. This is a very important idea. So look at this a few times. Make sure you've understood it. We will prove many results in CFT by starting on the plane and then moving to the cylinder, or starting on the cylinder, then moving to the plane. So the fact that we've got these 2 points of view that are related by a conformal transformation, so they're completely equivalent descriptions of the dynamics, is going to be one of the powerful tools in our toolbox. We'll continue in a moment.